Saxon's Calculus, Lesson 54, is about the chain rule and then equivalent forms for the derivative. Now, in an earlier lesson, I made a statement that we need to make sure that we are deriving every part of the formula, and I find that this is helpful to make sure that I've kept on track. But what they're doing in this lesson for the chain rule is they're saying we can create, and this is algebra, dy over dx if we have multiplied, and these dy's will cancel, du's will cancel and leave you the dy over dx. And so obviously this multiplication works. So knowing that, in example 1, it says, if y equals u squared plus 4u and u is the 5x cubed, find dy over dx. So to do that, we're going to follow deriving this part and then deriving the u part. So that's going to give us 2u plus 4 multiplying with the 15x squared. That's the deriving of both of those and multiplying them together. Now, I'm not finished with the problem because although I've done the deriving, I still need to substitute back in what this u was into the answer. So 2 multiplying with 5x cubed plus 4, and all of that is still multiplying with the 15x squared. Sorry, I don't know what's going wrong with my voice here. Now, we do need to do some simplification here. So this will be (10x cubed plus 4) multiplying with the 15x squared. Now this 15 needs to multiply with the 10, 150x to the, when I multiply bases, add exponents, x to the 5th, and the 15 times the 4 is 60 with the x squared. And again, I derived every single part of the problem and then I simplified it. Example 2, y equals the natural log, 2 natural log of v, 2 natural log of v, and v equals u squared. Find dy du. So we're going to derive, and our 2 with our natural log of v ends up being 2 over v, because the natural log of v is 1 over v. And then the derivative here is 2u to the first power. And that, if I simplify it, becomes 4u over v. And now the substitution I need to put in is for the v. So 4u over u squared. And the u over u, these are going to cancel one off and one off. So that just leaves me 4 over top of u. Example 3, if y equals the sine of t and t equals 1 over the square root of x, find dy dx. So we derive our sine goes to cosine, and then our t, now this one I need to fix before I derive it. This is actually x to the negative 1/2, the x from the 1 and the denominator number of 2, and negative because it's in the bottom. So now when I derive it, negative 1/2 x to the negative 3/2. I don't think I can, other than putting the negative 1/2 in front, I can't really simplify that. So let's just go ahead and do the substitution. Cosine of t, I think I am going to move that minus 1/2 out to the front, and then our, just a second. That was cosine of t. T is what I'm supposed to be substituting. This should be a parenthesis. Got distracted with my minus 1/2. So let's go ahead and put that back to 1 over radical x. And that was multiplying. So then I still need, I guess technically I should, to be precise, put this x to the negative 3/2 in front as well. yeah. I'll cram it. X to the negative 3/2, and then the cosine of the substitution. Sorry, that's a little tight in there. All right, then in part B, it's talking about the equivalent forms for the derivative. So we know that we have the original formula that used the change in x, and then we have that same formula with the h substituted for the change of x. And now they're saying we can say that if I am deriving an a, we can say that is the limit of x going to the a, and then we would have f of x minus f of a over top of x minus a. So it's just a slight change in the formula, but this is another way of asking for the deriving, this time with kind of the plugging in of the a into the formula. Example 4, use the new form of the definition of a derivative to find f prime of x if, that's what I want to find, then if f of x is x squared plus 1. So what we're going to do is plug into our new formula then, where our f of x used the x squared plus 1 minus, and now we're doing f of a, so everywhere I had an x, I'm going to use an a instead. So now that's a squared plus 1 all over top of the x minus a. All right, that's filled in. Then, can I simplify anything here? Or do I want to plug in the a? I want to simplify first. So x squared plus 1 minus a squared minus 1, if I distribute, means that the 1's have dropped off, and that just leaves me x squared minus a squared all over the x minus a. And since this looks like it might be a factor of this top, I want to factor the numerator. So x and x, a and a, no middle terms, so one has to be positive, one has to be negative. Positive times negative is negative, so we're good to go. And then the x minus a, they do cross off, and it just leaves me the x plus a. Now, with my limit, oh, I didn't write that in front. Over here, because I used this part, I didn't write the limit where it said x is going to a. I need to plug that a in where I have an x here. So a plus a ends up being 2a. Again, we like our shortcut much better, but that does work with the formula, and that's a good reminder of that. So in example 5, f of x equals x squared. Use the new form of the definition of the derivative to find f prime of 1. Did it say of 1 or equals? No. That's what I did. I instinctively wrote x. Yes, it's definitely 1, not x. Okay, now we're back on track. And they want you to do the new formula. It is so much nicer to not. Okay, in this example, I'm just going to derive it and not do the new formula, because the derivative is 2 to the x, and then x is plugging in as a 1. 2 times 1 is 2, and so it was just so much faster to get to the answer of 2. Now, I don't see anything in there working. It factored, it canceled, there was nothing new. Okay, example 6. If f of x equals the cubed root of x, use the new form and the definition of the derivative to find f prime of negative 1. Wrote the format right that time. Okay, even though I don't like it, I suppose I should follow their Oh, oh, it's so many fractions. Okay, I'm reading the very bottom of page 269 where it says problems like this one are carefully contrived so that students can find a solution using the skills and concepts they have studied thus far. If the function had been like the 14th root of x, the trick we used in the problem would not have worked. Okay, their trick was the fact that it was perfect cubes, and they did a perfect cube factoring. You know what? I am not going to use their lovely new definition. I'm going to do the shortcut again. So this would be written as x to the 1/3. And then technically at that point, that's where they started plugging things in. So they had x to the 1/3 minus a to the 1/3 all over the x minus a. Then, even though that was 1/3, they treated it as the perfect cube and factored it that way. Okay, but we are going to do 1/3 x to the minus 1 minus 3/3 negative 2/3, plug in -1, so 1/3 with -1 to the negative 2/3. Okay, I do need to fix that. So 1/3, 1 over -1 gets now the positive 2/3 as its exponent. Now, the exponent part is 2, so -1 squared to 1. The cube root of 1 is 1. So all of that's 1, and that multiplies to keep the 1/3 as the answer. Oh, that was so much faster than going through their thing. All right, part C of this lesson is the proof of the chain rule, which, since it is optional, you can follow how they do their plugging in and their manipulation of the formula, but I'm not going to walk you through all of that.